wearing mismatched ones. If I'm wearing pink on one foot, you instantly know the other one isn't pink. That's an ordinary correlation, but the spooky part comes later.
Imagine Alice and Bob, each given a sock from the same pair. If Alice sees pink, Bob must see blue. Always opposite, just like socks. That's the classical idea of hidden rules. But you see, quantum socks are different. If Alice and Bob both check in the same direction, they always find opposites. But if they choose slightly different angles, the pattern changes. They aren't guaranteed opposites anymore. Sometimes they match, sometimes they don't, in a way that follows a smooth curve. That wave is a cosine curve. The difference in their angle decides how strong the correlation is. At zero difference, perfectly opposite. At 90 degrees, completely unrelated, like flipping coins. In between, the chances slide smoothly. On the block sphere, we can picture this as two turning arrows by angles theta and phi. The socks don't decide their colors ahead of time. The act of measuring makes the result. Bell asked, if socks had hidden rules, what's the maximum strength these correlations can add up to? The answer? 2. It's like 4 tug-of-war matches. No matter how you stack the results, the total pull can't go past that ceiling. That's the classical limit. But quantum socks don't stop at 2. With entanglement, the wave-like correlations push past the total up to about 2.8. That's a violation of Bell's inequality, and a proof that the world doesn't work like ordinary socks. Anton Zeilinger and others put this to the test with real photons. A laser hit a crystal to create entangled pairs. One photon to Alice, one photon to Bob. But here's the key. Alice and Bob don't set the angles themselves. Random numbers made the choices on the fly. 0 meant the filter pointed one way. 1 meant it pointed another way. The switching was so fast, no hidden signals could pass between Alice and Bob. Later, Zeilinger's team even used signals from distant galaxies to pick up the numbers, ensuring the choices were truly independent. That's why Clauser, Aspect, and Zeilinger were awarded the Nobel Prize in Physics. Einstein called it spooky action at distance. Alice and Bob's socks revealed it. Particles don't just follow fixed rules, they dance with probabilities, and we're part of that dance.